Hello friends, I am Joy and I welcome you back to Krishna Coaching Academy classes. So in today's lecture, I'll be talking about a topic which is called the combination of capacitors. So let's quickly revise what is a capacitor. A capacitor is a device which is used to store electrical energy in a circuit. The most common way of, or one of the most common ways of designing a capacitor is called parallel plate capacitors, where we have two parallel plates separated by a small distance, as you can see in this picture. Now the capacitance of this particular setup called the parallel plate capacitor is given by epsilon naught A by D, where A is the area of each plate and D is the distance between them, and epsilon naught is called the permittivity of free space. So that means more the area we have of the parallel plates, more is the capacitance, and less the distance between the plates, more is the capacitance. Now the next thing we need to know is that if instead of air between the plates, if we replace the air by something called a dielectric, then the capacitance, the entire capacitance will get increased by a factor which is called K, known as the dielectric constant of the medium. Now let us have a detailed look at what is actually happening. When you insert a dielectric material like this, we know that the capacitor has a uniform electric field. A parallel plate capacitor, if we ignore the edges, towards the center it has a uniform electric field. That means, let's say if we ignore these edges, like for the rest of the capacitor, there is a uniform electric field from the positive plate to the negative plate, as a result of which the molecules inside this dielectric will get arranged in a fashion something like this. Now imagining that all these will be internally balancing each other, the last layer of this dielectric, that is near the minus Q plate, will have a positive charge density, and the layer which is near the positive plate will have a negative charge density. So as a result of which there is an electric field in the opposite direction, in the direction opposite to the original electric field, as a result of which the electric field that was initially between the plates of the capacitor, that has decreased because of the insertion of this dielectric, because dielectric has now its own electric field, that too in the opposite direction. Now we know that if we decrease the electric field, the potential will also decrease, and capacitance is given by Q by C. That means for a given amount of charge, if the potential is high, that means the capacitance is low, and if the potential is low, then the capacitance is high. So because of this dielectric, what is happening to the potential? It is getting decreased. So that means the capacitance of this will increase. So that is the reason why we have this factor K, where K is greater than 1. Means the capacitance is going to increase because of the insertion of this dielectric. Now let us look, instead of one capacitors, if we have more than one capacitors, then what can be the cases? One case is that we can connect all these capacitors in series, one after the other, as shown. We know that when we put a number of elements in series, then the voltage that we are applying across this, that gets divided. So the total voltage will be divided between the capacitors. This will be V1 plus V2, where V1 is the voltage across this capacitor and V2 is the voltage across this capacitor. So the total voltage drops will be equal to the given voltage. Now we know this from this formula, that C is equal to Q by V. So that means your V will be equal to Q by C. So applying that, we can say that V1 will be Q by C1 and V2 will be Q by C2. Now Q will be constant in this because, let's say if I take this portion, when there was no voltage, there was no charge in this capacitors. When we apply a voltage, this got negatively charged. How? It's because of this voltage, or some field is created and the electrons has moved from the rest of this part. See, look, this part is totally disconnected from the rest of it. So electrons has moved from this towards this plate. If 5 electrons has moved towards this, so this will become minus 5 and this will become plus 5. So hence these two will be equal in magnitude. That's the reason we are putting both these as Q. If this is the charge Q on this, the same charge will also be present as Q on the other plate, or for that matter, however, like whatever is the number of capacitors which are connected in series. Now, if we take the Q to the other side, it will look like V by Q is equal to 1 by C1 plus 1 by C2. This V by Q, we can imagine it to be one effective capacitor. It's like instead of these two, we are just drawing one capacitor. Okay, so this where V is the total is the potential difference across it, and Q is the charge. So in that case, V by Q can be called as 1 by C, and that will be equal to 1 by C1 plus 1 by C2. So from this we come to know that if we connect a number of capacitors in series, then the effective capacitance C will be given by 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3 and so on. As simple as this. So this is how we represent capacitors in series. Now let us look at the alternative case where the capacitors are connected in parallel. That means all these positive plates are connected and all these negative plates are connected. In the previous case, you will see that the positive plate is connected to the negative plate and so on. But here all the positive plates are connected to one point and all the negative plates are connected to the other point. In this case, you will see that the potential, when things are connected in parallel, the potential is same for all of them. That means the potential difference here and the potential difference here will be same, because this is the total potential difference. Okay, so here we see that both the potentials are same. The capacitance of these two are different, as I'm calling this as C1 and this as C2, and the charge that will flow is also different, because if some charge is coming this way, then some amount will go this way and some amount will go, or the rest of them will go this way. So the total charge will be given by the sum of the charges. That means if Q charge is coming this way, Q2 charge enters this capacitor and Q1 charge enters the first capacitor. So the total charge will be Q1 plus Q2, and we know that Q is equal to CV. From the first slide we know this, Q is equal to capacitance into voltage. Similarly, Q1 will be C1V plus C2V, because V will be same in all the cases. We can cancel the V's and we see that the effective capacitance is just C1 plus C2. As simple as this. So from this we know that when we have a number of capacitors which are connected in parallel, the total capacitance is just the linear sum of all the capacitance. So just we need to remember two things, that if in series the capacitance is 1 by C is equal to 1 by C1 plus 1 by C2 and so on, and when they are kept connected in parallel, the C is C1 plus C2 and so on. So with this, let us try to do one question which came in NEET in 2016. So it's not that, I mean, it's quite recent. So this talks about a parallel plate capacitor, but the inside of it has 4 different dielectrics, K1, K2, K3 and K4. The total area of this the parallel plate is A, such that it is divided into A by 3, A by 3, A by 3 in case of these 3 dielectric medium, and the distance D is divided into 2 layers, D by 2 and D by 2, where D by 2 is occupied by this first set of dielectrics, and the next D by 2 is occupied by one particular dielectric which has a dielectric constant of K4. What is asked in the question is, what is the relation between the effective dielectric constant of this capacitor with the individual dielectric constant. So just let me have a read at the question. A parallel plate capacitor of area A, plate separation D and capacitance C is filled with 4 dielectric materials having dielectric constants K1, K2, K3 and K4 as shown in the figure. If a single dielectric material is to be used to have the same capacitance C in this capacitor, then its dielectric constant would be. That means if we want to replace this, by one capacitor with one dielectric constant K, what is the value of that K? And there are 4 options given for the value of this K. Now let us analyze how the students will solve this question. So to make you understand better, like since assuming that you are the students who have just started your class 11 or yet to start, there will be 4 stages of students in solving these kind of problems. The first step, the first stage, which I call as kids, he will say that, well, I only know that capacitance is equal to epsilon naught K A by D. That's all I know, and I know that series is 1 by C is equal to 1 by C1 plus 1 by C2 and so on, and parallel is C is equal to C1 plus C2 plus this. And when there is lot of dielectrics organized like this, I don't have any clue how to do this problem. So I just give up on this. This is the first stage. I mean, you don't even know how to start with this problem because you only know some of the basic things and you don't know anything further. Then from this is the first stage that all of us were at some point of time. Okay, so let us go to the next stage, which I am calling as men. So he or she will tell that although this is one capacitor with different dielectric media like inserted at different proportions, this can be thought of as something equivalent to this, where this K1, K2 and K3 are three capacitors which are placed in parallel like this, and this entire combination that is in series with this K4. So this is what these three are in series with this. Now we have some clue how to solve this. Firstly, let's take these parallel set of capacitors. So the capacitance of the first capacitor, that is C1, that means of medium K1, that is given by epsilon naught A. Now A is A by 3 because the entire area was A. This K1 only occupies A by 3. Divide by D by 2 because the distance it takes is not D but D by 2. Epsilon naught A by D into K1. Similarly, the capacitance 2 will be epsilon naught A by 3 D by 2 K2, and capacitance of 3 will be epsilon naught A by 3 divided by D by 2 into K3. And since these three are in parallel, we can say that the total capacitance of, let's say, C parallel will be equal to C1 plus C2 plus C3. That will be given by, we can take epsilon naught A by D as common, epsilon naught A by D as common, then 2 by 3 will also be common, then it will be K1 plus K2 plus K3, as simple as this. Now these capacitors which are in parallel, they are in series with this capacitor called C4. So the capacitance of C4 will be equal to epsilon naught A. This is the total area A, but the distance is D by 2. So this will be divided by D by 2 into K4. So this is what we get. Now since these two are in a series, the total capacitance of this will be given by 1 by the total capacitance is equal to 1 by this C parallel comprising of these three parallel capacitors plus 1 by C4. Now this entire capacitor will have capacitance epsilon naught A by D, and let's say K is the effective dielectric constant of the entire capacitor. That will be equal to 1 by, if we go to the previous slide, this epsilon naught A by D 2 by 3, epsilon naught A by D 2 by 3, so sorry, this will be this one, 1 by C, it's not C, it's 1 by C, 2 by 3, this will be K1 plus K2 plus K3, okay, plus 1 by C4, so C4 will be equal to epsilon naught A D by 2 K4. Now if we cancel all these epsilon naught A by D from all the places, epsilon naught A by D from all these places, what will remain is, sorry, this D is 1 by K is equal to 3 by 2 K1 plus K2 plus K3 and plus 1 by K4. So if we take the 2 to the other side, we can write it as 2 by K is equal to 3 divided by K1 plus K2 plus K3 plus 2 by K4. So if we go back to the options and have a look, we'll see that this is precisely option C. 2 by k, 3 by k1 plus k2 plus k3 plus 1 by k4. Sorry, there was this 2, there was this 2, so there was this 2, so this will be 1. So this is the option C that we are getting. So this is how we normally do this, by calculating each and everything that needs to be calculated, and this is quite lengthy. Let's go to the third stage, which I am calling as legends. He knows that capacitance is directly proportional to K A by D. So more the area, more the capacitance, less the distance, more the capacitance, and so on. So, and he knows that these three are in parallel, and these three combined with this, they are in series. So instead of doing all these steps, all we need to do is write the final equation directly. That this will come with practice, that 1 by C, now we'll not write C, this will be 1 by K. And because we know that everywhere that A by D will be there, A by D, the total area by total distance, that will be there. Some factors, 1/2, 1/3, those may be there, but epsilon naught A by D, that factor will be everywhere, that you know from your experience. 1 by K will be equal to 1 by K will be equal to 1 divided by, now we are going to tackle this. This will be simply K1 plus K2 plus K3, because they are of equal dimensions, and area was 1/3 and distance was D by 2, so a factor of 2 by 3 will come. We can directly put this, plus this will be 1 by K4. The area is same, but the distance is this, twice K4. So from this we can write 2 by K is equal to 3 divided by K1 plus K2 plus K3 plus 1 by K4, which is option C. So just in 2 or 3 steps we can directly get to the answer, provided we are very clear about this, what is proportional to what and what is common. So this will come with experience. I mean, I don't expect that on the day of entrance you will write all these things, C1, C2, C3, then C4, C parallel separately, then all this thing. This is going to consume a lot of time. Better than this is this. We know that C is directly proportional to K. So the structure is definitely going to be 1 by K is equal to, these are in parallel, this and these are in series, and these constants will come based on what are the area and distances of your capacitor. So this is the third stage, which I am calling as legends. There is a fourth stage which I call as ultra legends. Now, when you reach this stage, you will not even do any calculation. Just by staring at the options, you can come at the right answer. Let me explain how. We know that when capacitors are in series, the structure of the final capacitance, that somewhat looks like 1 by C is equal to 1 by C1 plus 1 by C2 and so on. And when they are in parallel, then this C will be C1 plus C2 and so on. So when now if we look at this is K1 plus K2 plus K3 plus K4. This is a totally parallel structure. These constants 3, 1, they are differing because of the areas and distances of the capacitors being different. But if you look at the structure, it is something plus something plus something plus something. This is entirely parallel. Similarly, if you look here, this is also some K1 plus K2 plus K3 plus K4. This is also entirely parallel. These constants may differ because of the areas and distances getting are different, but the structure is A plus B plus C plus D. This also A plus B plus C plus D. So this is nothing but completely parallel structure. And if you concentrate here, this is 1 by A plus 1 by B plus 1 by C plus 1 by D. This is a completely series structure like this, 1 by C1 plus 1 by C2 plus 1. So 1 by something plus 1 by something, when you have, they are completely in series. So these two options are completely have a parallel structure. The last option is a completely series kind of structure. But if you look at the actual question, this has both parallel as well as series. This has both parallel as well as series. So A, B and D cannot be your option because they either have only parallel structure or series structure. C is the only option which has both parallel structure and 1 by something plus 1 by something, that is series structure. C is the only option which has both the combinations present. So without doing any calculation, without calculating any capacitance, just by looking at an option, you can say this is the answer. This will take you less than 10 seconds because you have not done any calculations. You are already ahead of your competitors. So hope you have enjoyed this class, and I'd like to thank you for listening to this class. See you again sometimes in the future. Thank you.